Friends, we will continue with the discussion on topic shear center. This is lecture 29 in module 2, where we are discussing some topics on advanced structural analysis under the NPTEL course title Offshore Structures under Special Loads including Fire Resistant Design. Let us continue with the example what we discussed in the last lecture. So, thin walled section of uniform thickness T and this dimension was indicated as B1 and this dimension is indicated as B, and this becomes my axis of symmetry. We already know that when a section has at least one axis of symmetry, the shear center will lie on this. Let us say this is my shear center C, where the vertical force will be applied to avoid twisting moment in the given cross section. From this point we take the offset of the shear center as E, and let us call this point as point A. If you look at the shear flow within the cross section, we know that this is V1, V2, V3 and V4. To find V1, we took a section which is Z from here and we derive that V1 is Vt B1 square by root 2 I B by 2 minus B1 by 3, equation number 1. Let us try to find the I value, which is moment of inertia of the entire cross section about the axis of symmetry. So, let us take this object separately. And we know the dimensions of this is B1 and thickness is T. It has got two axes. Let us say this is my UU axis and this is my VV axis, and let us say this my x dash axis. So, one can easily say that IU is B1 T cube by 12 and IV is T B1 cube by 12, and we know that this angle is 45 degrees. Therefore, I x dash can be calculated as IU sin square 45 plus IV cos square 45, which will be B1 T cube by 12 sin square 45 is 1 by 2 plus IV T B1 cube by 12 1 by 2, which tells me is B1 T cube by 24 plus T B1 cube by 24 dash. But I want to find about this axis the moment of inertia. So, Ix using parallel axis theorem will be Ix dash plus AK square, which I say B1 T cube by 24 plus T B1 cube by 24 plus B1 into T is the area and K is actually the centroidal distance of this from here. Okay, that is my K, which will be B sin 45 minus B1 by 2 sin 45. That is the distance, the whole square, which can be B1 T cube by 24 plus T B cube by 24 plus B1 T B by root 2 minus B1 by 2 root 2 the whole square, which can be B1 T cube by 24 plus T B1 cube by 24 plus B1 T B square by 2 plus B1 square by 8 minus B B1 by 2. So, expanding further, B1 T cube by 24 plus T B1 cube by 24 plus B1 B square T by 2 plus B1 cube by 8 minus B B1 square T by 2, which can be further simplified, because I have a term B1 cube here and B1 cube here. So, let us say B1 T cube by 24 plus T B1 cube by 6 plus B1 B square T by 2 minus B B1 square T by 2. Let us say this is Ix only of the component, let us say first component, okay, equation 2. Now, let us look back this figure. If I take moment about the point A, since V2 and V3 pass through this point, they will create no moment. Only V1 and V4 will create moment. The distance of V1 from this point will be equal to B. Therefore, we can take moment about the point A, no moments will be caused by V2 and V3. Therefore, no need to estimate V2, but we need to calculate the moment of inertia of the part 2 with respect to axis of symmetry, that is required. So, let us take part 2, which is like this. UU axis, and this is my VV axis. Say this is my x dash axis. And this angle is 45 degrees. So, we know now that, and the dimensions are this dimension is B and this thickness is T. Therefore, IUU of part 2, this is part 2, IUU is T B cube by 12 and IVV is B T cube by 12, I x dash will be I u cos square 45 plus I v sin square 45, which will be T cube by 12 1 by 2 plus B T cube by 12 1 by 2, which gives me T B cube by 24 plus B T cube by 24. So, I want to find I x x, where say this x x axis passes through this point. This may axial axis of symmetry, which I call as x x axis in this case. So, I should say this is I x dash plus a k square parallel axis theorem, which will be T cube B cube by 24 plus B T cube by 24 plus B into T is the area, and K will be B by 2 sin 45 the whole square, which gives me T cube B cube 24 plus B T into so which will give me so I have two BQ terms. Let us add this, which will be 4 T 24 plus T cube B by 24, which means T B by 24 4 B square plus T square, that is I x x of part 2. Now, I want to find the I x x of the whole section, which will be now equal to I x x of part 1 plus I x x of part 2 into 2. There are two such parts, which will be B 1 T cube by 24 plus T B 1 cube by 6 plus B 1 B squared by 2 minus B B 1 square T by 2, that is part 1, plus T B by 24 4 B square plus T square, now the whole multiplied by 2. Now, one can to find E, take moments about A, you are taking moment about this point So, I should say now V 1 into B, okay, V into E will be equal to V 1 into B plus V 4 into B, which is V 1 plus V 4 into B, which essentially is 2 V 1 into B. So, in this equation V 1 and B are known, E can be computed. Or on the other hand, V 1 is known in terms of V. So, therefore, still E can be computed. So, in this example we have seen how one can locate shear center for sections which has at least one axis of symmetry. Now, let us say to find shear sections or shear center, to find or locate shear center for sections which have no axis of symmetry, unsymmetrical sections. Let us take an example. Let us take this my unsymmetrical section I am drawing. Let us say this is my z axis and this is my y axis and that becomes my CG, which I need to locate, and the section has no axis of symmetry. Okay, let us mark the dimensions of the section. Let us say this is 40. This dimension overall is also 40, and this dimension is 20. The section has uniform thickness of 2 millimeters through and through. So, now let us call this distance as z bar and this distance as y bar. So, the first step is to compute z bar y bar, which are coordinates of the CG. So, we will use to find z bar sigma a z bar by sigma a. Let us say 20 into 2 area of the first part, this is the first part, and CG distance 10 plus 40 into 2. So, this is the part, second part, and the distance is 20 plus this remaining distance, this value will be 40 minus 4, which is 36. So, this is the third part, 36 into 2 into the distance of that from here is 1 divided by 20 into 2 plus 40 into 2 plus 36 into 2, which will give me z bar as 10.8 millimeters. So, this value is 10.8. Similarly, y bar is sigma a y bar by sigma a, which is 20 into 2 into 1, that is the distance, 40 into 2 into 39, that is the distance of that second piece, plus 36 into 2, the distance of this CG from here. Okay, we are bothered about this distance, okay, which will be 36 by 2 is 18, 18 plus 2 is 20. So, 20, okay, divided by 20 into 2 plus 40 into 2 plus 36 into 2. I get y bar as 23.9 millimeters. So, we have located the CG. Now, the next step is to find moment of inertia, which is I z and I y. So, from the first principles we can find I z as 20 t cube by 12 plus 20 into 2 into 22.9 square. If you look at this, we are interested in finding, let us say, this distance. Okay. So, 23.9 minus 1. So, 22.9 square, okay, that is what we are writing here, plus b d cube by 12 a k square. So, this distance will be 15.1. Okay. It is actually 39 minus 23.9, okay, that is what you get, 15.1 square plus 2 into 36 cube by 12, that is for the part 3, plus 36 into 2 into 3.9 square, because this CG will be from here, okay, 18 plus 2 20, this 23.9, therefore 3.9 square, which amounts to 4.82 10 power 4 mm 4. Let us find I y. B d cube by 12 plus a k square let us see, I am talking about I y. This is 20, so the distance is 10 and 10.8, so 0.8 square plus 2 into 40 cube by 12, 40 into 2 into 20 minus 10.8 square plus 36 into 2 cube by 12 plus 36 into 2 into 9.8 square. Okay. I get I y as 2.57 10 power 4 mm 4. I can also find I z y. I z y is summation z y d a for the whole area. So, let us do it. For part 1, 20 into 2 is the area and the z value and the y value, plus part number 2, 40 into 2, and the z value is minus 9.2 and the y value is minus 15.1 plus the third part into 2 is 9.8 positive and 3.9 positive. So, I get this value as plus 1.46 10 power 4. Please note that I z y can also be negative. Okay. Please understand this. In this case, it is positive. Once I know I z, I y and I z y, we can find out the inclination of the principal axis of inertia by this equation which we already derived. Tan 2 alpha 1 is minus 2 I y z by I z minus I y, which in my case is minus 1.46 10 power 4 by 4.82 minus 2.57 into 10 power 4, which says tan 2 alpha 1 is minus 1.298, which tells me alpha 1 is 63.81 degrees. So, let us try to plot this. So, this is my u, this is my v, and this angle is 63.81 degrees, which is alpha 1. It is a positive u. So, these are u and v are principal axis of inertia. Okay. Now, I can find them. I can determine them from the formal equation. I u is I y I z by 2 plus z minus y by 2 cos 2 alpha minus y z sin 2 alpha, which can be 2.57 plus 4.82 into 10 power 4 by 2 plus 4.82 minus 2.57 into 10 power 4 by 2 cos of 127.6 degrees minus 1.46 10 power 4 sin of 127.6 degrees, which tells me this value is 1.852 into 10 power 4 mm to the power 4. I can find I v as I y plus I z minus I u, which will be 4.82 plus 2.57 minus 1.852 of 10 power 4, which tells me is 5.538 10 power 4 mm to the power 4. So, I have I u and I v. Obviously, u and v being principal axis of inertia, I u v will be 0. Okay. I u v will be 0. Now, after locating the principal axis of inertia, our interest to find the shear center, we need to apply load V, that shear force, perpendicular to UU axis. So, let us say this is my object or this is my section. This is my z axis, this is my y axis, this is my u axis, v axis, this angle is known and these distances are also known. This is 10.8 and this is 23.9 and this value is 40, this value is also 40, this value is 20 and the thickness is 2. The shear flow is like this. Let us say this is my V1, this is my V3 and this is my V2. V3 and V2 intersect at this point. So, let us say I want to apply the force perpendicular to u axis, let us say apply it here, So, I am interested in finding out actually this distance. Okay. Interestingly, if I call this point as point A, by taking moment about of forces about point A, V3 and V2 will have no component. Okay. So, let us say only V into EU will be there. Let us cut a section. At the distance Z and the CG of the section is, let us say, V bar. So, V1 is tau dA, which is integral tau T dz. Tau is V A y bar by I t. In my case, it is going to be V A V bar by I u into t. So, which will be going to equal to V by I u integral A V bar by t into t dz, which will be V by I u integral z t, okay, into V bar dz. Now, interestingly, it is important to find V bar, okay, of the CG of the portion, this distance we want to find the V bar. We know V is actually equal to Z sin alpha plus Y cos alpha. So, if you look at any cross section, if I say this is my Z, this is my Y and this is my, let us say, dA, and these are my u and v axis and this is my alpha, then I can easily say I resolve this negative side of v, therefore, v is minus z sin alpha plus y cos alpha. Now, we would like to know the coordinates of this specific CG, okay, in terms of V bar. So, which will be minus of minus 20 minus 10.8 minus z by 2 of sine 63.81 degrees plus 22.9 cos 63.81 degrees. Okay. That is going to be my V value. Now, the question is why this is negative. You can see here this is 20, the CG of this point is on the negative side of z, okay. That is why it is minus. So, substituting minus 9.2 minus z by 2.9 plus 10.11, which gives me 8.28 minus 0.45 z plus 10.11, which will tell me 18.39 minus 45 z. So, now let us get back to V 1, which will be V t by I u integral 0 to 20 z into 18.39 minus 0.45 z of d z, which can be V t by I u 18.39 z square by 2 minus 0.45 z cube by 3, which can be V into 2 by 1.852 into 10 power 4 of 18.39 into 400 by 2 minus 0.45 20 cube by 3. So, one can find V 1 by equation 1. Once I know V 1, taking moment about A, I can say V into E u is V 1 into 38, because 38 is the distance of C g from this point to this point, that is this distance. So, V 1 is known in terms of V, therefore, we will cancel and E u can be determined. So, friends, the summary of all these 4 lectures: shear center is an important location for thin walled cross sections. If force does not pass through shear center, it will cause torsion in the cross section, and shear center is intersection of loading plane with the bending axis. If the section has one axis of symmetry, shear center will lie on this axis. We have seen examples to find out shear center for cross sections having at least one axis of symmetry, and also for cross section which does not have even any one single axis of symmetry. I hope you have understood these lectures and followed these examples. There are many more examples available in the literature. Please try to solve them and try to find out how you can estimate shear center location for the given cross sections. Thank you very much.